Hello guys, so today we deviate from the usual content because I want to tell you about this really interesting instrument I recently came across that is a really old amperometer capable of measuring down to 2 or 3 nanoamperes. Yeah, that's 10 to the minus 9 ampere, and this device works only by mechanical and optical ways without any operational amplifier or other modern circuitry. The only electrical part is a light bulb that can be turned on using a normal plug. So let's do that and open it and see how it works and how it's made inside. It's not easy to see the display with the light on the camera, at least by naked eye. It's really easy also in a well-lit room, so I'm gonna make it darker so you can see. So after turning it on, we get to see that there are two light spots displayed on the screen. By the way, the screen is just a ruler made with some marks that are a total length of 10 centimeters. In the front we only have one knob that we can move, and we can see that this knob moves the bigger dial that is on the screen. You can see how sensitive it's only to minimal movement. And by turning this knob we can change the position of the bigger dial that you can see in the center has a black line that is used to indicate the reading. So this is the front panel. While looking at the back, we see just one screw for disassembly, 3 connectors, and some data. So here, this is really interesting because we can see the sensitivity of this instrument, that is 0.0029 microampere for every millimeter. So for every millimeter of movement of the dial on the front, we get this current that can be measured by connecting the amperometer using these two connectors in series. We also get some other data like the parallel resistance that we can put between these two connectors in parallel of the instrument, so that the movement is lower and damped, and the period of the oscillation, that is 2.8 seconds. That means the time that it takes for a dial to make one full swing. So now let's go ahead and open it up and see how it works and what's the inside. So to open it, we just need to remove one back screws, and this whole part come off. And we get to see the beautiful mechanism inside. So this is the internal. Sorry for the blown image here on the side, but the metal is all painted with a really dark matte paint, so it's really hard to see on camera. The tube here contains the light bulb, the only electrical part present in this instrument. In fact, the electrical connections enters here and goes to this transformer that then feeds these two connectors on the side that powers up a normal 6 volt light bulb. the light created in this tube get focused by a lens inside of this other tube. The lens also contains a metallized layer with silver that is just a line centered in the middle of the lens. This way, the image that we saw projected on this screen could be easily created, just like that. The light is then projected from the lens onto this interesting piece right here. So this is where the measurement is taken, and here you can see a glass entrance window. This is used to let the light coming from the light bulb to get inside of here, where there is an extremely sensitive kind of galvanometer that rotates on about its axis when a force is present, and the same way the extremely small current of just a few nanoamperes flowing inside of this solenoid and on this magnet make a very small mirror inside of this cavity rotate about its axis. So the light comes in this way and is then reflected back by the mirror, and when there is a current the mirror is moved and the light beam is moved also, like this. But the movement is extremely small, much smaller than we could use, and so to multiply this movement a combination of mirror is used. In fact, the light is reflected from here to here. This is a convex mirror and reflects the light by enlarging the figure, and this way it gets the small movement of the galvanometer get multiplied, and the light is then reflected from the mirror onto the scale. So the scale is illuminated by the reflected beam, and we can measure the current by measuring the displacement from the zero position. And how we zero the instrument? Well, that's just by having no current flowing in it and using the screw we saw here in the front, the only parameter we can move, to just rotate the mirror about its axis. You can see by turning the screw the mirror moves a very little amount, and this way we can zero the measuring scale and position it or on the center or on one side, so that we will have enough room when the current is flowing to measure it precisely. There is also one last part in this instrument, that is this glass here. This is just a normal piece of glass, like from the one used in microscope, and it's placed between the reflective mirror inside of the galvanometer and the measuring mirror here that projects the image onto the scale. This mirror reflects the same image reflected by the galvanometer, but not amplified by the mirror, so that we will have also a second scale, which have a movement that is proportional to the current flowing in the instrument, but which his displacement is much smaller than the first scale. So this way we will have two measuring ranges. To center this we can use the knob here, placed on top of the galvanometer, and this sets the zero position of this scale. Okay, so to make a measurement with this instrument, we first of all need to adjust the zeroing position. To do that, I firstly use the calibration screw inside of the galvanometer, inside of the instrument, to get a coarse positioning, centering of these lines. After that, we can use this knob here to zero the position. In fact, as you can see, by turning it, we can move the main scale around and position it where we prefer. I'm gonna now position it here on the left 0, so that we have the whole range. Remember that this scale works by measuring the displacement when the current is passing. Every instrument has been calibrated at the factory, and this one in particular has a sensitivity of 2.9 nanoamperes per millimeter. So every little mark corresponds to around 2 nanoamperes. To make these extremely small currents, we need a really high value resistor. For this reason, I got this 1 gigaohm resistor made for high voltage measurements that we can use, and also this smaller resistor here. And I'm going to use just 1.5 volts from a AA battery. So using 1 gigaohm and around 1.5 volts, we should have around 1.5 nanoamperes. So a very small movement of the dial, not even one complete mark. So now I'm gonna connect it, and you can clearly see a small movement has appeared. It's not one entire mark, but a little bit less. If I use half of the resistance by connected to the middle point, you can see that the displacement almost doubles, as it should be. So now let's measure some lower resistance. So I'm gonna use now this 10 mega ohm resistor. I also cannot keep my hands connected between the two terminals, otherwise I will put this meter off scale. For example, if I now touch with one hand one terminal, and with the other here I touch the other side of the battery, you can see an extremely high movement, as even my skin has such a resistance that the small current passing is seen by the instrument. Also, this makes me able to demonstrate the use of the second scale. As I told you, this other scale here serves the purpose of giving a rough estimate of the current, as this moves around 10 times less compared to the very sensitive scale here. So if I connect now my hand around between the two polarities like I showed you before, we can see that the sensible scale goes completely off, while the coarse scale is still inside of the measuring range. And this way we can have a rough idea, as the coarse scale goes to around 30 millimeters, and considering that the coarse scale has around 4 microampere, sorry, 0.04 microampere per millimeter, we can get a rough estimate of around 1.2 microampere current flowing through my body with just 1.5 volts which puts my skin resistance at around 1 mega ohm. That is a plausible estimate. But now let's make some more accurate measurement. Now I'm gonna connect this 10 mega ohm resistor. You can see the dial oscillating with the period that we wrote in the back of the instrument of around 2.8 seconds, and it slowly stabilizes around a value 50.5 millimeters. So 50.5 millimeters times 0.0029 gives us a total current of 0.146 microamperes. So if we now measure the voltage of the battery, we can calculate an accurate value for this resistor value. So the battery measures 1.47 volts. So the resistance is just the voltage divided by the current, and we get a resistor that is pretty accurate, as it's 10.17 mega ohm, which is pretty good. Another simple demonstration we can do with this very sensitive instrument is just connecting a couple of turns of wire to the two terminals measuring the current, and then bringing close a simple magnet, and you can see that we generate a current. And it's also sensitive to the direction of the magnet, as if I bring it close this way, the needle moves to the right, and if I flip the polarity of the magnet, it moves to the other side, of course. Another very cool aspect of this instrument, I just realized, you can see it when I bring the magnet close and keep it still. Due to the Faraday law, this current should be zero, as the magnet is not moving. The magnetic flux in the wire is not changing in time, so there should be no current flowing. But instead you can see that it is indicating a current present that is slowly going towards zero. The reason is that inside of the instrument there is an extremely sensitive solenoid with a strong magnet. And so what I think is happening is that when the needle with the mirror moves and it tries to return back to the zero position, it induces a current flowing into the wire that then, by the Lenz's law, is opposed due to the presence of this closed circuit. As if I open the circuit, you can see that it goes to zero really fast, and if I close it, it locks in position, as the strong magnet inside hinders the rotation of the coil with the mirror. The same you can see happening using a small speaker. If we connect the two terminals of the speaker, you can see that just by gently touching it, we can make it move and go completely off scale. I mean, if I place just this little nut on top of the speaker, you can see it moves a lot. This principle could be used to make a very sensitive balance to measure weight, as for example with a a piezoelectric actuator. So in the end we saw this very interesting instrument that was used many years ago for very high precision measurement, for example of resistance, as it was used to balance bridges like the Weston Bridge. So if you have any other question, drop them down below, and bye.